I'm going to talk to you about the effect that motion has on MTF, and that motion can come in a variety of forms. There's linear motion, where the camera is moving in one direction, or there's jitter, where the camera is randomly moving in all directions with a Gaussian distribution to the amplitude of the motion. And then there's oscillation, which is like jitter, except it's in only one direction, and it's following a sinusoidal amplitude distribution. So if you're imaging a circle, for example, and there's linear motion, the image might look like this because that circle shifted over on the focal plane array a little bit during the integration time. Or if there's jitter, it might look like this because that circle is shifting in all directions during the integration time. And if there's oscillation, it would look like this because it's only in one direction. Looks like jitter in one direction, but it still doesn't look like jitter because jitter's amplitude has a Gaussian distribution and this is a sinusoidal amplitude distribution, so they are different. In all three cases, integration time is the key. The longer the integration time, the worse the effect. So how does it affect the MTF? Always as a product. The MTF is not any one of these functions. The MTF is a measure of contrast, and it's a consequence of the optics, the detector, the motion, and other things that we can cover as well. And each one of them degrade the contrast. Aberrations and diffraction degrade the contrast through the optical MTF. Sampling degrades the contrast further through the detector MTF. Motion degrades it even more. And the motional MTF can be divided into three factors, one for linear motion, one for jitter, and one for oscillation. So to describe linear motion, imagine an aerial camera. It could be mounted on an aerial vehicle, or it could even be on a satellite. Oh, let's just say a satellite. It's moving with some v, and in some amount of time, the ground sample distance completely moves over one ground sample distance. And at the same time, then the light that is being imaged by the ground sample distance shifts over 1 pixel. Let's define some variables. The altitude is h, the pixel size x of p, the focal length EFL, the ground sample distance GSD, and also the instantaneous field of view, keep this in mind, is the pixel size divided by the effective focal length. That ratio will come up later. The satellite moves, and in one integration time it moves a certain distance, which might be more or less than what's shown in this picture here, but the result then is a blurred image. After it has moved one ground sample distance, the image of the ground sample distance has moved 1 pixel. An illustration shows how that works. Looking at these two before and after pictures where the camera has moved over enough that the ground sample distance has moved over exactly 1 ground sample distance. Now the rays from the edges of this GSD on the left still get captured, but they get captured this way. They get moved over 1 pixel. And if the camera displaces again by 1 ground sample distance, rays will move over 1 more pixel, and so on. Every time you have a 1 GSD displacement, you have a 1 pixel displacement. Now how this degrades the MTF has a lot then to do with the detector because pixels are involved. In fact, it is detector MTF where this figures in. The effect that motion has on the MTF is the same kind of sync function that the detector has, because whether you're talking about motional MTF or the detector itself, you're talking about the effect of sampling on image quality. So let's deal with this argument. The portion in blue, speed, integration time, focal length divided by altitude, is the distance that the image moves on the focal plane array because the GSD moved. So that is the smear. That's how far the image of this GSD moves as the integration time elapses. Have you ever wondered how is it that a satellite that's moving at 7,000 meters per second can take images of the ground with any reasonable integration time? You'd think it has to be a very short integration time considering how fast it's moving. But this ratio of EFL over H is the key to that. The quantity V delta T over H is the angular displacement because V delta T is that. So this is that angle. And that angle is also found up here. And so if you multiply that angle by EFL, you get this length, the distance that the image of the GSD moved on the focal plane array. So this ratio for sure is a very small number on account of the fact that you're at a high altitude and you're using a camera with a focal length on the order of centimeters. Because sampling is actually the issue here, I want to rewrite the thing in blue in terms of the pixel size. So set V delta T EFL over H equal to some constant n times pixel size. And I want to talk about this constant. It becomes physically meaningful to us. What we have here when I say n times the pixel size is actually talking about n divided by the detector cutoff spatial frequency. So keep this expression and let's unpack what it means. Let's analyze n. There's a limit to what n can be. If it's huge, then that would mean that the image of the ground sample distance has smeared a long ways on the focal plane array. N for sure is something you want to keep small. Let's talk about how small it needs to be. There's that blue portion of the argument. Rearrange it to solve for n. V delta t in the numerator has a physical meaning. It's the displacement of the camera in one integration time. Divide that by h, you have that angle. So n literally is the displacement angle divided by the instantaneous field of view on account of x sub p divided by effective focal length being the instantaneous field of view. So what does it mean then if, say, for example, n equals 1? If n equals 1, the light has moved entirely 1 pixel over because in that case the angular displacement theta equals the instantaneous field of view. If n is less than 1, it's moved less far. So my interpretation of this coefficient n is it's the number of pixels that the image displaced. It's the number of pixels of smear. You could also look at it as the number of instantaneous field of views the satellite has displaced. So if the contribution of linear motion to the MTF is a sinc function, it's straightforward then to figure out a cutoff frequency for linear motion. Set that MTF to 0 and find the spatial frequency where MTF equals 0. That's the case when you're looking at sine of pi in the numerator, so NF over F detector has to be 1. If you're going to say that equals 1, then go ahead and rename the spatial frequency F sub Lm, the cutoff frequency for linear motion. Rearrange for it, and the cutoff frequency for linear motion is 1 divided by this n times the pixel size. So if the linear motion cutoff frequency is the detector cutoff frequency, n will be 1. If n is less than 1, then the linear motion cutoff frequency is larger than the detector cutoff frequency and it's detector limited, assuming it's not optically limited. And if n is greater than 1, the opposite is the case, and it's motion limited. I think it's good to graph this and see what it looks like. It should look a lot like the detector MTF, which it does. I normalized the spatial frequency to the detector cutoff frequency and graphed it from that normalized quantity equal to 0 to equal to 1. What's nice about this as the normalization is it has a physical meaning. F is line pairs per millimeter. 1 divided by the detector cutoff frequency is x sub p. It's millimeters per pixel. Cancel the millimeters. This is literally the line pairs per pixel. And that's why it's a useful normalization to use when looking at MTF, to get universal behavior like we're doing right now. When n equals 1, that's when the detector cutoff frequency equals the linear motion cutoff frequency, and that's where you are. If n is greater than 1, linear motion is really smearing your image. I want to bring up something about sine. In an MTF that's a sinc function, whether it's linear motion or detector, they're originating from the same argument. Some authors put in absolute value markers around the sine in order to keep this positive. I guess the feeling that because it's the modulus of the optical transfer function, it shouldn't be a negative number. But letting the negative numbers creep in there indicates something about phase. But if you put the absolute value signs there with detector MTF, you need to put it there with this because they're coming from the same argument. The point that I want to make is if you get to a negative MTF, the physical meaning is inverted contrast. That means that if you're originally trying to image this pattern, What you see on the detector is this pattern. Pixels that should have been illuminated are dark. Pixels that should have been dark are illuminated. That's inverted contrast. Yeah, so when you get to this, whether it's like this or like this, when we use absolute value on the MTF, either case, what's going on in that portion of the spatial frequency domain is inverted contrast. What's light is dark and what's dark is light. It kind of doesn't matter because the MTF is so poor at this point that you're not really getting useful information anyway out of the image, but that is what it means, inverted contrast. So you have to think about integration time, because if that's too long, you can expect a smeared image. So take this expression for n and then rearrange it for integration time. N is how many pixels the image of the GSD has moved over in one integration time. Then it's how many pixels you've moved over in one integration time. The rule of thumb is that if n is less than 1.25, then you won't have unacceptable image smear. And that's measured by the NIRS rating, which we haven't covered yet. That's coming in Module 9. If n is greater than 1.25, then NIRS loss will be greater than 0.1. NIRS measures image interpretability, and NIRS loss of 1 corresponds to a factor of 2 loss in resolution, roughly. Let's take a look at what a satellite that's creaming by at 7,000 meters per second is limited to with integration time. If the satellite happens to have a camera with 5 micron pixels and a 20 centimeter focal length, the maximum acceptable integration time in order to avoid resolution loss is that 4.25 millisecond. It's not tiny. It's on the range of integration times that are used in digital cameras. There's a size to that smear called delta x. So if you have these two neighboring pixels, and the first pixel is getting the light from the GSD illuminates one pixel, then that light moves over because the camera moved some distance, delta x. If delta x is less than a pixel, n is less than 1. But if it moves over an entire pixel, it looks like this. I change the shade of red to indicate the old light and the new light. These two pixels have captured light from the same GSD within the integration time because n is 1. So what you see is the smear then, with the light that should have all been parked on this left pixel is now parked on both pixels. And if n equals 3, the light will move over 3 pixels in one integration time. The smear will be like this. And was meant to be a factor that multiplies the pixel size to give the displacement of the light on the pixel. So delta x is n times x of p. N is a measure of how many pixels the light moved over in one integration time. So let's go back and set this equal to v delta t over h times effective focal length and calculate the image smear given a speed, an integration time, a focal length, and an altitude. And you get 6.25 microns with these numbers that correspond to that satellite that's going at 7365 meters per second with integration time that we just calculated to be 4.25 microseconds. And you'll notice 6.25 microns is exactly 1.25 times the 5 micron pixel that was given in that calculation. Jitter is random. And because it's random, you'll see effect in all directions. So rather than just getting thicker here and here, like it does with linear motion, it gets thicker everywhere because it's a random shaking of the camera relative to the object space. It makes sense to say that it's only jitter if the motion occurs in a time that is short compared to the integration time. If the motion in jitter occurs in a long time, then it's really linear motion.